The chip inside every AI data center costs more than a car, and 80 billion transistors is only the third most impressive number in it. First comes the price, $40,000. Second comes the precision, 5 nanometers, which is 1/20,000th the width of a human hair. Third is the transistor count. But here's what actually matters. None of those numbers explain why this chip exists or why it costs what it does. Let's start with what you're actually buying when you pay $40,000. You're not buying silicon. Silicon is sand. It costs almost nothing. You're buying access to a machine that costs $20 billion, and that machine can only be built in 3 places on Earth. The interesting part is that this isn't about the chip itself. It's about the factory that makes it. A chip fabrication plant, or fab, is the most expensive machine humans have ever built. A single fab produces 100,000 wafers per year. Each wafer is a circular disk of silicon about the size of a dinner plate. On that wafer sit thousands of chips. The math is brutal and simple. Divide $20 billion across 100,000 wafers, and you get $200,000 per wafer. Divide that across thousands of chips per wafer, and suddenly $40,000 per chip starts to make sense. But the factory cost is only half the story. The reason the chip costs $40,000 isn't the silicon, it's the clean room. During fabrication, engineers etch features so small that visible light can't even see them. They use extreme ultraviolet light, which has a wavelength of 30 nanometers. The features they're etching are 5 nanometers. A single dust particle, invisible to the human eye, scatters that light and ruins the entire pattern. One speck of contamination destroys millions of dollars of work. That's why fabs maintain clean rooms 10,000 times cleaner than a hospital operating room. Workers wear full bodysuits. Air is filtered through HEPA systems. The clean room isn't a luxury, it's the entire cost structure. Here's where it gets interesting. The actual transistor itself costs less than 1/1,000,000th of a cent to manufacture. The infrastructure around it costs everything else. One fab produces 100,000 wafers per year. That's roughly 1 billion chips. Spread a $20 billion factory across 1 billion chips, and you get $20 per chip just for the building. Add the equipment inside, the power consumption, the yield loss from contamination, and suddenly $40,000 becomes reasonable. The reason the chip costs $40,000 is infrastructure, not material. Now here's a question that might seem obvious but actually isn't. Why don't we just build more fabs? The answer reveals something fundamental about modern manufacturing. Building a fab takes 5 years. It requires expertise that exists in maybe 500 people on Earth. It requires supply chains for equipment that only 2 companies manufacture. It requires a stable government, reliable electricity, and access to ultra-pure water. The reason only 3 companies make advanced chips isn't because they're better at physics. It's because the barrier to entry is so high that it's economically impossible for anyone else to compete. The interesting part is the yield mathematics. A fab doesn't produce perfect chips, it produces chips with defects. Modern fabs achieve a yield of about 95%. That means 5% of chips are unusable. Those defects come from contamination, from quantum effects at 5 nanometer scales, from variations in the etching process. Engineers design the chip knowing that 5% will fail. They build redundancy into the design. They test every chip before it ships. The $20 billion fab is designed to tolerate failure at scale. What matters is that this entire system exists because of one thing: demand. AI data centers need these chips. Google needs them, Microsoft needs them, OpenAI needs them. They need thousands of them. They need them now. That demand justifies the $20 billion investment in a fab. That demand justifies the 5-year construction timeline. That demand justifies the expertise of 500 engineers. Without that demand, the entire system collapses. The reason we have $40,000 chips is because we have a use for them that's worth $40,000. But here's the thing that actually keeps the system running. The chip is only useful inside a data center. A single chip does nothing. It needs power, it needs cooling, it needs networking, it needs storage, it needs software. A single $40,000 chip inside a data center generates heat like a blast furnace. Thousands of these chips in one room create thermal loads that would melt conventional cooling systems. That's why data centers are built near rivers and lakes. That's why Google pumps water through underground pipes to cool its servers. The chip is the most expensive component, but it's not the bottleneck. The bottleneck is cooling. The reason data centers consume so much electricity isn't that the chips are inefficient. It's that they're doing work. A single kilowatt of power in a data center processes roughly 1 million tokens per second. That's not waste, that's the entire point. 10,000 servers in one building generate enough heat to warm a small city, but that heat is the byproduct of computation. You can't separate the two. The reason data centers exist is to do computation at scale, and computation at scale requires cooling at scale. Now let's talk about what happens inside the chip itself. The $40,000 chip contains 80 billion transistors. Each transistor is a switch. It can be on or off. Billions of these switches working together perform the calculations that power AI. But here's the mystery. How does a 5-nanometer transistor even work? At that scale, quantum effects dominate. Electrons tunnel through barriers they shouldn't be able to cross. The laws of physics that apply at human scales break down. The reason engineers can make this work is through material science and quantum mechanics. The interesting part is the material underneath. These chips aren't made of pure silicon. They're made of silicon with carefully engineered impurities. Engineers add boron or phosphorus atoms to change how electrons move through the material. They create layers of different materials, each one nanometers thick. They etch patterns so precise that a single atom out of place ruins the entire structure. The reason this works is that at 5-nanometer scales, you're not building with atoms. You're building with quantum probability clouds. You're designing structures where electrons behave like waves, not particles. What matters is that this level of precision requires testing at every step. Engineers can't just build a chip and hope it works. They test the materials. They test the processes. They test the finished chips. They run statistical analyses on millions of chips to understand failure modes. They use electron microscopes to examine defects. They use X-rays to see inside the chip. The reason we know these chips will work for years is because we've tested them at scale. The reason we know they'll fail in predictable ways is because we've studied those failures. The reason the chip costs $40,000 is because it represents the cutting edge of human manufacturing capability. It's the most complex object humans have ever mass-produced. It contains more transistors than there are stars in the galaxy. It operates at speeds that would have seemed impossible a decade ago. It does all of this while consuming less power than a light bulb. The reason it costs $40,000 is because we've invested $20 billion in the infrastructure to make it, and we're spreading that cost across millions of chips. The reason it's worth $40,000 is because AI data centers need it, and they're willing to pay. But here's what actually matters. The chip is just the beginning. The real engineering challenge is building a system where millions of these chips work together. That's where the real cost lives. That's where the real complexity emerges. The chip is expensive, but the data center is exponentially more expensive. The reason data centers exist is because the chip makes them possible. The reason the chip costs $40,000 is because the data center justifies it.